Okay. Hello everyone. Today I'm going to talk about like fast optimization from linear program to semi-definite programming. And this is a joint work of like a bunch of co-authors by He Huang, who is like an undergrad student from Peking University, and he's going to apply for grad school this year. And Shunhuan, Renzhou, and Hengjie, they are from like Columbia. They are PhD students right now. Yeah, the picture from Renzhou and Hengjie is from like they are going to some like IOI computation while their teammate didn't show up. That's why they are only 2%. And that's also Armin Winston is their advisor. Let me start. So today's talk we will mainly have 3 parts. The first part I will explain some motivations and some techniques from very high-level picture. What does this technique mean? And then like the second part I will focus on linear programming, and the third part I will just focus on semi-definite programming. So usually, what is optimization? Optimization can have 2 parts, and in one case it can have you can work on like a convex optimization. On the other hand, sometimes you need to work on a non-convex optimization. The major difference between convex and non-convex is in convex optimization, you only have like one minimizer, but in non-convex optimization, sometimes you have a local minimum and also set of points. But the major point is whenever you work on like this function, either convex or non-convex, you use the roughly same method. So here, let me tell you the method. You give a function f, and your goal is to like find some parameter w, such that the f of w is minimized. This is a very basic goal. And what we do in general is we first initialize a weight that w0 to be random weights. And then like we do some greedy type of algorithm. Every iteration, we update wt to wt plus 1 by using the gradient information. And the running time of this algorithm has 2 parts. So the first part is called like number of iterations. And the second part is the cost per iteration. Usually it has to be the input side of problem, which means like in every iteration, you have to read the input side of problem. So naively, if you just combine these 2 parts, and the running time will be t times c, where t is the number of iterations and c is the input side of problem. So now the question is, can we actually do better? So is there any way like we can just read the input once by paying like a times c, and then like every iteration we only need to pay like small o of c. So ideally, if capital T times small o of c is less than capital C, then like you can hope to get some running time, just input side time. The major observation we use to getting all this time is something called like the weights is changing very slowly. Mathematically, it means like the delta Wt is approximately sparse or low rank in every iteration T. Because once you have this like observation, therefore you can just try some like compression idea, for example, like a sampling or sketching.
Sorry, could you remind me what W of t was again?
Wt is in neural network, like in deep neural network, it's just a weight between all the layers somehow. It's just a parameter of the problem. It can be very general. Yeah.
The t is just an increment by 1. It's the number of steps you're taking, right?
Yeah. Yeah.
So normally you might write that as a subscript.
Oh yeah, that's a good point. Yeah. Because sometimes we use subscript to select the columns of W. Therefore, like we put a bracket T here.
Thank you.
Yeah.
Sorry, one more question. I know it's possible in some algorithms for linear programming and whatnot that C is that the iteration time is super linear in the size of the problem, right? So is C here the input size, or is C here the iteration time?
See here the iteration time. But I'm just saying like in the most cases you have to pay like input side of problem. See you should think of say the iteration. Yeah.
I see. Okay.
Yeah, that's a very good question. Yeah, but once we go to later talk, it's very clear. Yeah, what I mean. Yeah. So now I will just like give you some like a brief introduction of linear programming. Linear programming is one of the most like representative example in convex optimization. It has many applications like energy industry, and transportation system, food and agriculture, and also like efficient manufacturing. So the linear program is a very simple question. You have like a given like a matrix A and a vector B and a vector C. You want like solve the following optimization question. There are solvable problems. It can be written as LP, and this is also known as one of the top 10 algorithms in the last century. Another very primitive example, like in non-convex optimization, is called like deep learning, where like usually you give some data like x1 to xn, and also they are labeled y1 to yn, and you want to like solve the following like a minimization question, and the phi here is nonlinear activation function, and the weights a1, a2, a3, they are the parameter of the neural network, which you can think of, which are like WT from my previous slide. So there are some problems on current Earth can be solved by deep nets. And of course, this could be one of the very important algorithms in the century. So today I will give you I will tell you some motivation from how to use some motivation from deep learning and to actually improve some algorithm in like a linear program. So the first half of talk, I will mainly focus on implement techniques like plot observation, like the weights are changing very slowly, and also some streaming sketching techniques. And then I will tell you how to use this idea to get you a faster solver for several fundamental problems in the field of optimization. For example, like linear program, LP, semi-definite programming, SDP. And at the end of the talk, I will show you some very promising and interesting future direction to work on. So let me start with what's the high-level ideas behind those algorithms. The first idea is called slowly changing, and the second idea is called sketching. So what's the meaning of slowly changing? Think of if you have a dog, you have to walk the dog, and all during COVID-19, your kid cannot go to kindergarten, you have to take care of them. And the major similarity between these two pictures is when human, either you are taking care of dogs or taking care of kids, and most of the time you don't need to move too much, you don't need to put too much energy, and you just need to make sure the kids and the dog, they are not walking too far. And the major similarity between the two pictures is something the same strategy used by human in two pictures is something called lazy. So in practical deep learning, and for example, if you have a neural network, you want to classify either image is a cat or a dog by using this one hidden layer neural network. And so if you plot the weights between all the layers, and you will see they are very small. If you ever train neural network and actually plot these weights between two iterations, you will see they are very small. So also in deep learning theory, and this slowly change has been implicitly used in math. Let me give you some brief introduction of this one hidden layer neural network. So in order to make a neural network working, we also need some nonlinearity. For example, an iteration function, which is ReLU here. ReLU is a function which is take the input and you take the max between input and 0. It's basically a truncation function. And now I'm going to introduce the weights. And here I use the W sub R to denote the R's column of weight matrix W. That's why I use the T in the bracket and use R in the subscript. So if you look at the first hidden node, in the hidden layer, and you draw all the connection from input layer to the hidden layer, you will see their weight. We call the weight say W1. And usually we say a neuron is fire if the inner product between the weight WR and your input image is 0 or bigger than 0. And we say non-fire is below than 0. So the major observation we have in the training of neural network theory is the number of neurons that they change their states are very small. The change in states means you either a neuron is changing from fire to non-fire or from non-fire to fire. Here is a concrete example. Let me draw all the connections between input layer and hidden layer. And so suppose I'm at time step t, and then like the weights like between like a input layer and hidden layer is called WT. And I use the light color to denote a neuron is unfire, non-fire, and I use the dark green color to denote a neuron is fire. At time step t, there are only 2 neurons are fire, the node 2 and node M. And once you go from like a WT to WT plus 1, the third neuron will become fire, and all the other neurons, they don't change their states. And then you move to the next iteration, WT plus 2, the last neuron will be on fire, and all the other neurons will be not change their states. That's in some sense explain what I mean by slowly change in theory. So in next few slides, I will explain another like tools called like sketching.
Sorry, I have another question.
Yeah.
Could you go back through what it means for the problem, whether the neurons are on fire or not?
Yeah. So the neuron like is fire means like if you look at WR times X is bigger than 0 because you are looking at loop right now. And then non-fire means like the neurons like inner product between the image and WR is below 0. Because if you are always on fire, your value is just the same, just to be 0 forever. And if you are fire, like your entry is greater than 0. Is that clear to you?
And what is the output? How are the hidden layers connected to the output?
Yeah, you just draw a fully connection edge to there. You draw like every edge between for every output layer, like you draw a connection between the hidden node and output node. So there are
and there's also a ReLU sitting at the output.
No, in the output you don't have ReLU. I mean, this is like a very tall example, like in like it's just like a very classical theory model we use, like it's called like a 2-layer neural network or 1 hidden layer neural network. This has been like using like a few hundred papers like to study neural network. And in practical machine learning, and the output layer, they are like if you want to do like usually if you do MNIST or say for 10 or say for 100, usually the output the number of nodes in the output layer is the same as number of classes you have. So if you want to like classify image into 10 classes, you have 10 nodes in the output layer. And here I'm just giving a tall example. Yeah. Any other question in the slides? Okay. So now I will tell you like the idea like a sketching. So if you Google this word, and usually it means like you give a picture and you draw some like boundary or something. And here is a picture like from Dickerson. And one sketch could be like another picture where like every pixel is his co-author. And this is another picture of a boy. And here is a sketch. You just draw the boundary. And the sketch, of course, like if you do a sketch, of course, you will lose a lot of information from the original picture, for example, color or details. However, if you look at a new picture, and you still can roughly tell who is this person. That's a major point of sketching. Sketching also have some like a very specific meaning in numerical linear algebra. This idea originated from like Saros, like then like in Clarkson and the Woodrow paper, they provide very nice results like input sparsity time for solving linear regression and lower approximation. And later, like David read the book and survey a lot of problems which can be done in this way. So here I will just like briefly tell you what's the meaning of a sketch and solve in math. So usually the question is following, I give you a matrix A and a vector B. And let's say like A is much bigger than D. Your goal here is to find some X such that AX is roughly equal to B. So formally, we want to like minimize AX minus B, L2 norm is small. So this is just called like a very standard L2 regression formulation. You can also change this 2 to be 1 or P, then it's called like L1 regression or LP regression. But for now, let's just focus on L2. Let's assume like we have a L2 regression, sorry, A. And now what we are going to do is let's choose a sketching matrix. So usually sketching matrix is more like a random Gaussian matrix and very fast. And let's say like the s is much small s is much like it's just much smaller than n and more like poly d log n. So what we need to argue is the following thing. We need to argue like the solution to the sketched version of the regression question is actually a very good approximation solution to the original L2 regression. Therefore, like you can just run a server on a sketch version of the problem, and then you are done. So one important remark I want to make here is usually the way we use the sketching, we just use the sketching as a black box. We just apply to the data. We don't modify the solver. So using the sketch and solve idea is enough for you to solve many very important questions, for example, like linear regression and low rank approximation. And today, like I'm going to explain like how to combine like the sketching and also slowly change. And this time, like we need to actually modify the solver. And I will show you two results. One is linear programming, and the second one is about like a semi-definite programming. So let me start with like a linear programming. So I will first remind you definition. You give a matrix A and vector B and a vector C. Let's say like they look like this. Your matrix A and vector B is going to like decide a convex body in 2 dimensions, like here. And your vector C is going to decide the angle of a line in 2 dimensions. And now in order to solve LP, what you need to do is you just need to push this line until you touch the boundary of the convex region. Then we solve LP. So solving linear programs has like a very long history, like almost 200 years. And the first algorithm for solving linear program is a very famous algorithm called simplex algorithm. This algorithm is developed by Zhao in 1947, around like a Second World War. And this algorithm is very efficient in practice. Even right now, like people are still sometimes use this algorithm. But the best thing of this algorithm is this algorithm takes a plenary time in theory due to the clean meeting counting example. So then there are like a long-standing open question. Is LP actually in P? So until like 1979, Lin Kachin proposed a new algorithm called ellipsis method. This is the first like polynomial time algorithm. And after this algorithm, we know like LP is actually in P. But the weakness of this algorithm is very slow in practice. So no one uses this algorithm. Even like even this algorithm has a theoretical guarantee, like we still use simplex algorithm. Then there is another like a very interesting question. Is there some way to design a LP algorithm which like runs in polynomial time in theory and also very practical? So in 1984, there is an algorithm called like interior point method. This is an algorithm developed by Karl Marker. And this algorithm takes polynomial time, is running also like a very efficient in practice. And so currently when people are solving LP in practice, sometimes they use simplex and sometimes they use this interior point method. One like a very important advantage of this like interior point method compared to the ellipsis method is like your like interior point method only take root iterations, while ellipsis method take n iterations. And therefore, like most of the follow-up work who are trying to like improve the running time of linear program, they are mainly like built on the interior point method. So the first like LP algorithm, like over the last 30 years, is due to like Vaidya, and his algorithm is the fastest one, takes like n to 2.5 for the dense 4-rank matrix. The n to 2.5 is somehow very nature because like you have like root iterations, and the input size of probably is n squared. So therefore, like he need to like pay like n to 2.5. And two years ago, in a joint work with Michael Cohen and Intel Lee, we actually show this algorithm. We actually gave an algorithm which is much faster than n to 2.5. It runs like n to omega plus like n to 2 plus 1/6. in today's talk, I will show you like how to actually improve this 1 over 6 and why improving this 1 over 6 is very important. So in a very recent work with Shenhua Jiang and Almer Winston and Hengjie Zhang, and we actually improve this 1 over 6 to 1 over 18. And here, let me briefly like remind you what's the meaning of this running time. So omega is the exponent of matrix multiplication. And n to omega means like the time for multiplying an n-band matrix with another n-band matrix. So currently, omega, the best omega is 2.37286. And this is due to a very recent result at SODA by Josh Ellman and Virginia Williams. So in our community, and some people actually believe like omega is actually equal to 2. So one reason is like over the last many years, the best lower bound we know is due to run and runs, which is only n squared log n. Now I would like to justify why like this algorithm is essentially tight. And because the point is, even like if you want to solve like a linear system AX equal to B, the major difference between solve linear system and LP is in LP you need to have this C transpose X, and in linear system you only have AX equal to B. The best algorithm for solving linear system takes like n to omega time. So in a very recent work at SODA, and Richard Peng and Santung and Pala, they show that for some like a matrix A, if your matrix A is sparse and well conditioned, and then like there is actually hope you can actually develop the linear system algorithm which is even faster than n to omega. However, like for the worst case, like some linear system, the best we know algorithm we know is still n to omega. So because like some people believe like omega should be 2, then you may ask like what if omega is 2? Like at that time, linear system takes n squared time, but like LP still only take like n squared plus 1 over 18 time. So here another like a recent follow-up of our paper. Since our paper is online for 6 months, and yeah, because like when we are writing these papers, we are rushing the deadline, and we didn't think about like how to like make the paper shorter, and our proof is quite long, like it's more than 100 pages, and there is a paper like by Young Brander, and he actually can simplify like a small part of our algorithms and can like somehow reduce like our page, reduce like 30 pages of our proofs in some sense. But currently we still don't know how to do a shorter version, very short version, like 50 pages somehow. So even like combine all these results, like so there's a very interesting open question, I think, which is still open, which is like, can we actually solve LP as a fast as linear system for any omega? Like more concretely, like can we actually improve this like 1 over 18 to 0? Yeah, this seems like at least to me is a very hard question, because I have been thinking this how to like improve like 1 over 18 like for a long while, but I don't have any progress. Yeah, but I do believe like solving this problem is very interesting, because like this technique is also can be applied to many other optimization questions, for example SCP and other things. Any question here? Okay, here I will like give you a brief history of the solving linear system and linear program. The x-axis is a year, and the y-axis is the equivalent of running time. And solving linear system boils down to doing matrix multiplication. The naive algorithm takes NQ, and the Strawson algorithm beats the NQ bottleneck. And then there are a long time people believe like maybe like n to 2.5 is the right answer. But until like the Cooper-Smith and the Wignall tensor construction, as you can see from the picture, over the last 30 years, the progress of this question is very slow. So linear program at the beginning takes equation time, and then like we know like how to optimize running time, and the best algorithm for the last 30 years is n to the 0.5. And I do want to like mention here in Lee Seyfert paper, they do improve the LP a lot for the case when matrix is sparse or low rank. And however, for the worst case, dense and full rank case, their algorithm remains n to the 0.5. And 2 years ago, we have a paper. We actually can show like for the current omega, we can solve LP as fast as the linear system. And for omega equal 2, our algorithm will run like n to 2.16. And in recent work, and we improve this 2.16 to 2.05. As you can see from picture, the gap between like 2 and 2.04 is actually very tiny now. Yeah, in a recent in this year, there are new work. They improve the like measure multiplication exponent, like but as you can see from picture, this picture you almost didn't see any change from the picture, but they do get some improvement. So now I will like give you some like ideas of like how the LP techniques work and how do we actually improve it. Okay. So LP boils down to an iterating algorithm, and it has routine iterations. Every iteration it involves like several like numerical linear algebra computations. For example, you want to multiply a matrix with a vector, or you want to do matrix multiplication or matrix inverse. So in the rest of the talk, I will not explain why does algorithm suffice to solve LP. I will just focus on present the permutation bottleneck and tell you guys how to actually improve those bottlenecks. So here is the oversimplified algorithm of Vaidya's 1989 algorithm. And say like I is the number of iterations, I is the iteration counter, and at the beginning we initialize with W. And we have while loop. And in line 3, we compute some H, which based on very cheap oracle, take W as input. You should think like this line 3 takes 0 time. And then we need to compute the matrix P, which is the inverse of the constraint matrix times diagonal of W times the constraint matrix again. And compute this like a P matrix takes like n to the omega time, roughly. And then what you else need to do, you need to compute you need to update your W, and by like using like a P times H. And the P times H is the matrix vector multiplication. This takes n squared time. And then you increase the counter and you finish while loop. So naive implementation of this algorithm takes n to the omega plus 1/2. Because you have routine iterations, every iteration, the bottleneck is from line 4. And however, Vaidya do something non-trivial, which only takes n to the 2.5. So the cost per iteration of this algorithm, like line 4 gives like n to the omega, and line 5 like give you n squared. So as you can see, like even like a Vaidya can improve the n to omega to n squared, it's still unclear how do you actually improve the n squared, because this n squared term is actually from like 3 different parts in every iteration. You want to like get n to omega time, you do need to remove all these 3 bottlenecks. So therefore, like whether you can get the small of n to 2.5 time is open like for almost 30 years. And in the work like joint work with the Cohen and Lee, and we actually get n to omega time. And in today's talk, I will like first describe previous ideas, then I will show you how to improve 106.
So Zhao, question for you. So you don't need P otherwise, right? You only need P times H.
What do you mean otherwise?
So in your algorithm, the only the P is only used to compute P times H. Is that correct?
Yes.
Okay. And H is changing over time?
Yes.
Okay. Thanks.
Yeah. So as you can see, this is an iterating algorithm, and A is fixed forever. W is changing over time, and H is changing over time. P is changing over time. The point is W is changing very slowly. Therefore, like H is changing slowly. P is also changing slowly.
Okay.
That's like the thing we are going to use to improve the algorithm eventually. Yeah, that's a very good question. Yeah, I like to mention like in some other application of like optimization, you are not just using P times H. You also use the diagonal of P. For example, cutting pulling method or something else. I think in STP you need to use P to do something else, but let's just focus on LP for now. Yeah. Okay, Let me briefly remind you what is the compression techniques. So we are going to use some randomized compression techniques. So called sketching. Your sketching matrix can be a very dense matrix. Each entry is random Gaussian entry, and the matrix is very fat and only have root and rows. And sometimes there are also other sketching matrix you can see more from this book. And there are another sketching matrix called a sampling matrix. And the major difference between sampling matrix and the sketching matrix is the sampling matrix D is just a diagonal matrix, which only have a B non-zero entries on a diagonal. But essentially, they can perform something same. They can perform the same property. But for some tasks, those two matrices, they do have different behavior. And since the major computation we care is actually P times H, and the right way of doing sketching or sampling is we plug in the sketching between P and H. For example, we put R transpose R inside the two terms. And as long as in order to make the algorithm work, we need to make sure at every iteration, we can control this error. So there are also some other deterministic compression technique. And so they can actually maintain the H by not just saying put the sketching. And here are three four works. And they are all the four papers, they are using different techniques. And the weakness of all the papers is all of their papers, these papers, they are stuck at 2 plus 1/6. None of the paper can go beyond this 1/6. So the first paper is the first N2 omega paper in the joint work with Cohen and Lee. And this paper we use some sampling technique, and we put the diagonal matrix D between the P and H. And in the second paper, we put the sketching matrix and on the left-hand side of P. And in the third paper, we put the sketching matrix between the P and H. And in the last paper, Brandon used some vector maintenance idea to actually handle the H vector. With his algorithm, most surprising thing in Brandon's paper is his algorithm is a determinist algorithm, because whenever you do a sampling or sketching, your algorithm has to be randomized, and Brandon can actually give a determinist algorithm for a 2 plus 1/6. Yeah. So now I will explain our lazy algorithms. Let's define P of W, which is this inverse of constraint matrix times W times constraint matrix. And let's say we have an input sequence. Think of this as a streaming question. For some person give you a W1, W2, and WT, and you know every WI they are close, and you also get H. And what we know in math is WT minus WT plus 1 is actually nearly sparse. So nearly sparse means most entries are very tiny, only a few entries are huge. And your goal is the following. Whenever you see a vector W and you want to modify W to some vector V, and you want to make sure the W is close to V, and also in the meantime, you also want to make sure the difference between the VT and VT plus 1, they are actually exact sparse. This exact sparse is very important to design some optimization algorithm when you're using compression techniques. The guarantee you hope is some function of VT is close to some function of WT. This function can be many things, like identity projection matrix or projection times H. So here is a concrete example. Say a W is a dog and V is a person. And you're when you walk with your dog, and you need to use leash. And the leash has a limitation of length. You cannot hope every dog is like this picture. It can take care of himself. So therefore, human has to use a leash and to take care of either dog or kid and make sure they are not lost or hurt. But in the meanwhile, you also want to do something else. For example, writing some papers or doing research. And therefore, you need to do a smart maintenance thing here. So here is a more concrete example. Let's say this is the initialization location of the dog. And at the beginning, you choose your human location to be this blue ball, just same location. And when your dog is moved, and when leash is going to break, human need to move. When leash is not going to break, human doesn't need to move. So sometimes like when dog move, human move, sometimes human doesn't move. So eventually, if you draw like the length of the trail, total length of the trails between the blue balls, which are the human trails, it will be much smaller than the length of the total trails for the dog moves. And therefore, like that's how we actually eventually argue the running time is below like n to the 2.5. This is basically the major idea in Cohen, Lee, and Song paper. So here I will give you like a brief summary of the running time. Like in the Cohen Lee paper, they get like n to omega plus n to 2 plus 1/6, and they use some like the changes are changing slowly. And say like this is dog, and you have a Superman to chasing a dog, and when dog is moving, like Superman is moving, and eventually you prove like the total length of blue lines is more than orange lines, then you get this like n to omega time. And in our new paper, like we are not using the changes are changing slowly. We are also using the changes of the changes are changing very slowly, which is the second order of the changes. Let's say this is a dog, and we not only have a human, we also have a children. So now the task is going to be more complicated. Your child need to take care of the dog, and human need to take care of the dog and child at the same time. For example, when dog can move, and this time like child move, but human doesn't move. But when dog can move, and this time child move, and human also move. And eventually, the same thing, you need to prove like the total length of the trails is much smaller. That's how you like improve the bottleneck from 106 to 118. This is basically like the high-level idea of our new paper. So here I will just give you a summary of the running time, like how I actually get this running time. So
Zhao,
yeah,
sorry. So could you give a, that was very high level. I don't know if I actually got sort of any idea of what you guys are doing. So can you say maybe a couple more sentences about what the ideas are?
Yeah, I think the next slide will be very clear. So yeah, I will say something here. So this is the optimization question, but how to speed up this optimization question, it boils down to design some data structure. The data structure usually we learn from undergrad class, it has two parts, like an update and a query part. So in the Cohen Lee S paper, we have a data structure, we only have two stages. One stage is called update, one stage is called query. And update, you should think about how you update the V, and query, you should think about how you compute P times H. And eventually, when you balance the query part and update part, that's how you get like a 2 plus 106 term. And in the new paper, we basically design some like a more complicated data structure. And the data structure have two levels of update. So the point is sometimes we need to do a full update. Sometimes we need to do only need to do a partial update of the V. And in the query part, and then the running time will reduce a lot. And at this time, when you balance three terms, like you will actually get some improvement. That's like the major, like the high level idea of the things. Is that enough, or I should say more words?
Sure, that's fine. Thank you.
Yeah. The whole paper is very complicated. I try to like give some like intuition instead of going into too much details. Yeah, sorry about that. But I'm happy to talk offline if you just shoot me an email after the meeting. That's fine.
Great, thanks.
Yeah.
So I was under the impression that practical code for interior point methods are lazy. How does it relate to yours?
Yeah, that's a very good question. So in practical, like interior point method, I don't think they're using the lazy idea. And also like I'm not sure like I'm not totally sure in practical like interior point method is a good way to solve LP. But before like last few weeks, I was trying to like implement SDP algorithm. I do see like in Python like a package, the SDP algorithm they do use like interior point method. So I don't think the current implementation they use lazy idea. And also I'm not totally sure if my algorithm can be like made very practical in a short time, but it could be a very long time game in some sense. And we found some like interesting application of non-convex automation, like where like you combine the lazy idea with like something called like locality sensitive hashing, because locality sensitive hashing is very practical, and so combining this lazy idea with like a fast information location, it's unclear if it will be very practical in the future, but I'm planning to explore it. Yeah. So in the next few slides, I will show you the SDP thing. So like for solving linear system, we take n to omega time, and the input size n squared for omega equal 2, they are matched. And for solving LP, it takes n to omega plus n to the 2 plus 1 over 18. And input size time is also n squared here. And for current omega, it matches, and for the future omega, it's not. And for solving SDP, the question is what's the running time? The input is very different between like LP and SDP. In SDP, we have like M matrices, like each of them has size n by n. And you need to like the object function is you want to maximize the C column X, and also X has this PSD, and also AI dot X is BI. And the input size of this question is mn squared. Okay. Here I want to emphasize that SDP result is only optimal for m equal to m at least n squared. Because like for the other regimes, it's unclear what's the right answer even. Like both Intel and I we thought for a while, I think for other regimes, it's very hard to say what is the answer. Yeah. So SDP has like so many applications like in TCS and also machine learning. And one very famous example is like a mascot algorithm. Like it's a very famous, so I think everyone knows this thing. And SDP also has many other applications, and also like in learning, and also in discrimination, even like also in adversarial machine learning. And another important application is like if you like use like some squares to solve problems, like usually you can write like a SDP formulation. So here I will give you like a concrete application and concrete application for SDP, and I will give you some sense like what's like a difference between like LP and SDP. Give you some like basic like intuition. So there's like in kind of neural network deep learning. So there's an important question like called adversarial machine learning. So we know like a neural network can classify a dog and a cat. For example, if the picture are very nice, and how about these pictures? And how about these pictures? And do you think like a neural network can classify like are these pictures a dog or cat? Probably not. And also, how about this picture? You modify someone's face, and then neural network think this person is not like a person anymore. It's probably like 14% a dog. And most surprising, like there is something called like a misclassified by just changing one pixel. Here, this is a dog picture, and if I just change one pixel, and it's like a neural network will tell you this is a cat. And for human, you can't see the difference. And also, like there are more like important crucial application, like for example, like for stop signs. And when the time like going, like the stop sign will become bad, and some color will be gone, and then like the neural network will tell you this is not stop sign anymore. If you design some automatic driving system, and the car will hit human, this is going to be a very crucial issue. So adversarial example question can be designed the following: we have a set of images with labels, and you train a neural network. And for one image, and neural network predicts a cat. The question we want to ask is how much we need to modify this image such that the neural network will tell you this is not a cat anymore. This is a very clean and math question. And the math formulation can be designed the following. And I give you a function f, and for some input x0, you're going to output some smallest r such that there exists like a x prime in this ball such that like a fx prime is not equal to fx0. Here, like f is your trained neural network, and x is your image, and if x is your cat, our network says 1, and otherwise says 0. This is very like a simple math formulation of the question. So to solve this question, it has been proved to be NP hard if you want to solve this exactly. So over the last couple of years, there's a very famous work by due to like Cotter and Wang from like a CMU. And they actually give like their idea is very simple, but it's very cool. They actually relax this like it's an NP hard question to LP and give very good performance in practice. And also in another work, and someone also relaxed this question to SDP. So the major difference between like a LP and SDP is like SDP give you like a much higher accuracy, and compared to LP, and but in general, like SDP takes much longer time than like LP solve. So it's more like you are trading the accuracy with the running time. That's a game between like LP and SDP in practice. So there are also some other SDP solvers, and our work is mainly like focusing on second order method. So the major difference between second order and first order is in first order method, we only use gradient information, and in second order method, we use hashing, which is a P matrix in the slides. And also like in the first order method, the number of iterations is usually 1 epsilon. And for the second order method, the number of iterations log 1 epsilon. For some like important applications, epsilon can be exponentially small. Therefore, like using like a second order method is really important sometimes. So there are a very long list of work focusing on first order method. And so those works, they can be run very faster than like our paper, because they are using like a first order method. They are epsilon, but their epsilon dependency is bad. And also like there are works develop like a parallel SDP solver, and also like even quantum SDP solver. So here, let me like briefly introduce our results. So like I emphasized before, like SDP have some 2 parameters, one is m and one is n. Like for the case like m is below than n square, the running time will be like a little bit ugly, and but we still get some improvement. But for m at least n square, which is has a lot of applications in graph, and in this case we do get like m to the omega time, and this m to the omega is actually essentially tight, because you want to, if you want to like invert a matrix, it has to like take n to the omega time. Sorry. So m to the omega is the time of multiplying like m by n matrix with another m by n matrix. And in this new paper, actually like my original talk at SMU, my original talk plan is I want to talk about like from LP to deep learning. But the last 2 weeks I gave a talk like in January, like someone asked me, can I actually generate idea to LP to SDP? Then I work very hard with my students, and we actually improved it. We actually get this new result. That's why I changed the talk in some sense. Yeah, so we can actually solve this SDP as fast as current LP solver. This is also the first time like we know like SDP can be run as fast as LP, because like in the community, like we sometimes like believe like SDP is a powerful thing than LP, and maybe like there, at least like in terms of like formulating problems, we know like some problems, some approximation problems, if you use SDP and LP, their like approximation ratio or intergraph gap is very different. But like in terms of running time, we also believe like before like SDP like could be run much slower, like at least a root factor slower than LP. But in this paper, we show like you can actually solve SDP as fast as LP. Yeah, our results only works. Our results like we only get m to the omega when like m at least n square. For the small term, for m to the m less than n square, like we even don't know what is the right answer. Like yeah, here I would like to give you like a brief history like of the SDP, and there are a number of previous results, and the results of like SDP are mainly like 2 lies, and the first lie is using like cutting plane method, which is called CPM here, and the second lie is called like IPM, which is interior point method. As you can see from the table, and at the beginning, this algorithm runs very slow, like more like n to the 9 or n to the 8. And our work, we actually can bring down to like n to the 2 omega, because in the table, we only consider m equals n square. So therefore, like we use like the running time we eventually get is n to the 2 omega, which is roughly like n to the 4.746. Yeah, here just like a brief like a big picture of history of linear system versus like semi-definite programming. So as we all here is like just the history like I showed you before, like for the linear system, and there is a very new result like they improve the factor a little bit. And for the SDP at the beginning, we know like it get this time, and then we can run faster. Yeah, the table, and then like in our like in our last year Fox paper, we get something like a very close to 2.5, and now like we get this in this paper we get like n to the omega, and if omega equal 2, and our result will stop at n to the 2.25, which is 1 over 4. As you can see, like this 1 over 4 is much bigger than 1 over 18. I think it also could be interesting question to improve this 1 over 4. Currently, we are still trying to work on it. But because of like for LP, you cannot remove like 1 over 18 to 0. So therefore, like for SDP, like you also couldn't improve like 1 over 4 to 0. But you could get some, you could have some hope to get some improvement, I think. But we don't know what should be the answer right now. Yeah. So let me give you like a brief summary. We saw like a linear system, like it takes like n to omega time. This is the best algorithm we know, and has been many years. And we can solve LP like in n to omega plus some n to the 2 plus 1 over 18. And we can solve SDP in n to omega plus n to the 2 plus 1 over 4. And there are like a lot of very interesting future directions, I think. So first, like is like all the progress, like the major reason why like people didn't use these lazy ideas in progress optimization is the following. Over the last many decades, most of the optimization algorithms, they are trying to improve the number of iterations because the number of iterations is not even tight. But in the last 10 years, most algorithms, the number of iterations, they are becoming tight now. And therefore, like there is a motivation, you should actually try to improve the cost of iteration if you want to improve the algorithm. So I think it's a very nice direction if we can try to make this algorithm practical. And also like there are also some other recent work using similar ideas. They can like give some like graph from LP optimization. They can solve like a matching and flow like in like m plus like n to 1.5, where m is the number of edges and n is the number of vertices. And also it's very interesting if you can generalize this idea to some other convex like a setting. For example, there is another. So after I solved like SDP, I checked some literature. There are some other some like programming called hyperbolic programming. There are the actual conjecture whether these two programs are similar or like equivalent in some sense. So also like it's very interesting to generalize the idea to non-convex optimization, for example, deep learning. And also like in like this year, like in a Soda Bassoon paper, Hao Tianjiang, he actually have an optimization paper like for lattice related optimization. It's also interesting to see if this lazy idea can be used for those like a lattice-based like optimization question. And another like a very important observation I recently observed the following, like the major observation I use like in all these algorithms is like something called changing very slowly. And one of the advantage of quantum algorithm is actually it can get benefit from like doing sparsity search. And so if we actually modify the nearly sparse to exact sparse, then you can hope to use some quantum like a speed up. So I think it'd be interesting to see like if you can actually use quantum like a solver, quantum like a machine, whether you can actually beat this n to omega like in some reasonable way. And also like all this line of works, they actually like open some new questions for like a major multiplication field. So here like is a summary of the most of my works and also other works. And this is just a lazy update summary. And this lazy update can be used in many questions. For example, like LP and the empirical minimization and cutting plane and the SDP and also neural network. And the object you are trying to do the lazy thing is it can be different, it can be vector and block matrix and the PSC matrix and also multiple vectors. And the tools you need to combine, which is usually in most of our works, theory works, we just use fast multiplication. And we use like omega, alpha, beta, gamma. They are different parameters from fast multiplication. And in that recent like iClear our paper, we use we instead of combining like combining this lazy update with fast multiplication, we combine with locality sensitive hashing. So we do believe this lazy update framework is very practical, but the major thing like stop us is maybe like a fast multiplication. So therefore we try something else, and we use this LSH, and we can get like a six times speed up in practice. So all these likes works in like emphasize some importance for those parameters for multiplication. For example, like omega, which multiply n by n matrix with another n by n matrix, and alpha, which is n by n matrix, is n by alpha matrix, and the time you want to take you only allowed to take n square. And for n to the beta, which means you are not happy with n to the small one, you only want polylog time blow up in square. And also like there are some like n to the gamma, which is the time you can only pay like n square. And also like in the SDP paper, we use some like omega function, which like is very general like a term like a parameter function. Like for omega of 1 is equal to omega of alpha is equal to 2. We also need like omega of 3 somehow. Yeah, that's it. Like thanks for attending the talk, and feel free to ask any question. Yeah, I'm sorry for late for just 1 minute, and yeah, next 2 days is Chinese New Year, and hope you guys enjoy it. Yeah, feel free to ask any questions. Yeah. Hello.
Yeah, thanks for the talk, Zhao. Yeah, does anybody have any questions or? I think I asked all the questions that I had during the presentation itself. So
Yeah, if any, I can also open more if you, I don't know. Yeah, I think another thing I can emphasize is the following thing. This lazy update idea like only give you speed up for the number of iterations is huge. For example, at least like n to the c, where c is a constant. And if the number of iterations is only like a polylog factor, then you cannot hope using this idea to get some speed up. Yeah, that's something like very important. Yeah. And also like we don't know how to like apply this idea to first order method, because first order method is not like as robust as second order method. So currently we don't have any progress on generalizing these ideas for like first order method. I think it could be also very interesting direction.